doing that, I'll start the Zoom. So if you don't have it yet, there's a notes packet up here that we'll be going over today. It's on GitHub. It's the notes linear.pdf file. Are there any more quizzes that I should have? Okay. Yeah, so note packet up front if you want the physical copy, notes-linear.pdf in the 04 folder if you want the electronic copy. And so quick recap of a quick recap of our timeline, what to expect coming up. That again, we'll be finishing all the material between today and the Wednesday after fall break for your next midterm. And then so expect to have the next midterm 2 weeks from now, last week of October. And so far, what we've been talking about, we've sort of been focusing on statistical things, building up to this VC generalization bound theorem, which hopefully everybody has totally memorized and just barfed back onto the paper for me. And the idea of this theorem, again, is that this E out thing, this generalization, or this true error, this test error is the thing that we really care about for all of our algorithms. E out is what we care about, but it's something that we can't measure. It's something that the universe knows, but we're not the universe. We are puny humans, and so we don't know what it is. All that we can do is we can have some samples and we can measure this in sample error, this E sub in right here. And then we have this whole framework that we've built up for comparing, for knowing how different E in is going to be from E out. And that's the generalization error. This bound over here is referred to our generalization bound because it's how different our in-sample and out-of-sample errors can be. And this VC bound, it holds no matter how we select this, our particular hypothesis, our particular function that we are going to learn. And so the idea of the next 2 or so class periods is we're going to figure out how can we learn a hypothesis that's going to minimize this E sub in right here. That if we minimize the training error and this thing over here is kept small, then that is also going to minimize our out of sample error. And so this notes packet, and in particular chapter 3 of the textbook, is our first attempt of doing that. I feel, let's see, before we get into like the meat of the notes, I feel a little bit bad that this has so much text in it. It's a lot to look at, not very pleasing to look at on a big screen. So I apologize for that, but most of this is going to be notation stuff that is like almost exactly the same as the things that we've seen before, and just very, very slight differences. And so I'll highlight what those slight differences are. Anytime, so as a instructor picking a textbook, there's always like various trade-offs between different textbooks. And one of the things that I like about this textbook, the reason that I picked it, is because it has by far the simplest explanation of the VC dimension. And I think that's the most important thing, the thing that students struggle with the most. And so I wanted the best explanation of that for you all. The downside of that, though, is, or the reason why it's simple, is because it has a lot of concrete examples. The notation is as concrete as possible. But the downside of that is that as we move on, the notation changes as things become a little bit more general. So all of this notation that is on this page that we'll be talking about is the more general, slightly more general versions of things that you've already seen. So it should seem roughly familiar, but also maybe just a little bit different. Okay, so our motivation. So recall for a model, what a model is it's a hypothesis class plus a training algorithm. So people sometimes informally refer to just an individual algorithm or just an individual hypothesis class or a model as sort of synonyms for each other. But in the textbook, a model specifically implies both a hypothesis class and a training algorithm. And so far, we've just been focusing on this hypothesis class for our infinite dimensional hypothesis classes. Again, a reasonable idea for a training algorithm, though, should be to somehow minimize this in-sample error, this E sub n, because if we minimize that by our VC generalization bound, that is going to minimize our out-of-sample error. This formula right here, or in particular, this G hypothesis, is very often called the empirical risk minimizer. I'll write that out. Empirical risk minimizer. It's not, this particular phrase that I've written out here in blue is not something that the textbook says ever, but some other things that we'll be seeing, especially after the second midterm, use this phrase. And so it's a good one to know. And I might accidentally say it a couple times during lecture. And the empirical risk minimizer, often abbreviated as the ERM. And the reason that this is called the empirical risk minimizer is because this EN variable, again, EN, sometimes called the empirical risk. The risk being a synonym for the error, and empirical being a synonym for the in sample. It is not empirical like empire, like we've conquered the error. It is empirical like science, run experiments, actually observe the world. So all of these things are synonyms for each other. And again, one of the annoying things about data mining is that there are so many like equivalent terms for different things that people throw around, and you just have to know that they're all equivalent to each other. And so again, it's the minimizer because we're taking a minimum over here. We saw a long time ago when we were talking about finite hypothesis classes that there's this really simple algorithm, this try everything algorithm. You just compute all of the possible hypotheses and take the best one. And that works in finite time for a finite hypothesis class. But if we have an infinite hypothesis class, that's not going to work. And so the goal of this section is to figure out how to do this for an infinitely sized hypothesis class. Any questions on the motivation or any of that? Okay. So now getting into this new notation before we get into the fun stuff. So our notation, our new term here is a loss function. And this loss function, L, has two input parameters, this y hat. I'll pronounce this caret on top of the y as a hat. This y on the left is wearing a hat. This y is not wearing a hat. And it is a function that measures how bad the output of a hypothesis is. So the one without the hat, this is always somehow going to represent the true output. So what our true loss function is outputting of that f function. And then this y hat is somehow, anytime we see a hat, it's like estimated from data somehow. The hat means that this value is estimated. So this is the estimated output. And in particular for y hat is going to be equal to whatever our particular hypothesis is of some particular x. The x doesn't have a hat on it because it's not estimated. It's somehow given to us either in our training sample or test sample, or somehow that's given to us. But this h is sometimes called, so we know it's called the hypothesis, sometimes called an estimator. So it's an estimate of our what the true y variable should be. Then the in-sample error. So we already you just barfed out a definition for the in-sample error, but this is now the in-sample error with respect to a particular loss function. And so we still have this sum 1 over n from I equals 1 to n, somehow comparing, again, this right here is like the y hat. That's the y hat, somehow comparing these estimated values to the true values, but now in this generic version based on the loss function. And similarly down here, the true or out of sample error is based on the probability distribution rather than based on this sample. And if we were to take this function right here, often called the 0-1 loss, because its only possible values are 0 and 1, then and plug that into here, then you'd get the exact definitions that you had before on the quiz for the in and out of sample errors. What we're going to be doing over the next couple pages of these notes, though, is exploring different of these loss functions. And we'll see they have different computational properties. They are going to be easier or harder to do that empirical risk minimization. And we'll also be comparing their statistical properties to the 0-1 loss in order to know what our 0-1 loss is going to be. Any questions on this notation? Again, before we get to the fun stuff. Okay. Question? Yeah, I just Question is an example of a loss function. This right here is the only example of a loss function that we've seen so far, the 0-1 loss. And it's called 0 or 1 because the only output values are 0 or 1. It's equal to 0 whenever these two things are equal to each other. So whenever the correct value is equal to our predicted value, and it's equal to 1 otherwise. So this next section is going to lead us into our next example of a loss called the square loss. And yeah, again, this is all abstract, generic. Hope seeing more examples of loss functions will make all this hopefully get a little bit more concrete. Going a little bit out of order of the textbook, they start obviously with section 3.1 instead of 3.2. But we'll see the motivation for that here in a little bit. So all the problems that we've seen so far have been binary classification problems. So binary classification because the output, the thing that we're trying to predict, is either +1 or -1. Here, we're going to take a look at a regression problem. And in a regression problem, the goal is to predict a real number instead of a binary class label. So our output is going to be a real number instead of just + or -1. The most popular model for regression is called ordinary least squares regression, also often just called linear regression. They're essentially synonyms for each other. And it's called linear regression because the hypothesis class is the linear hypothesis class. It's a linear hypothesis class because this is a linear function. That right there. A linear function of the input x. Whenever we're doing regression problems, the 0-1 loss doesn't really make sense because we're never going to, or very rarely exactly predict exactly what the real number should be. And so instead, the squared loss is commonly used. This is the definition of the squared loss right here. And the idea of the squared loss is that if our prediction, so y hat again is our prediction, if it's close to y, so if y hat somehow approximately equals y, if they're close together, then our loss will be small. But if they're far apart, so y hat is somehow not approximately equal to y, then the loss will be large. And there are other loss functions that have this sort of similar property, but this one is just a particularly convenient one and very commonly used. If we plug, so this loss function right here, this equation 6 up into our equation 2 up here, so this general formula for the in-sample error, or the empirical risk, or the empirical loss, or the in-sample risk, all those terms equivalent to each other. If we plug in this value up in here, then we get this right here. So everything to the right of this first equals sign is the result of plugging in, substituting equation 6 into equation 2 gives us that. So yeah, you see the summation, all that stuff is the same. Here, this part, that's our y hat. That's the thing that we are predicting. And the yi, the true value right here, the y hat corresponds to this xi transpose w, and the yi corresponding to this y right here. And then all this summation stuff coming from equation 2 right above, coming from this. This is not the most, well, let's see. This form over here and this form over here happen to be equivalent to each other. And the textbook goes back and forth between these two forms and just assumes that it's easy to see why these two things are equivalent to each other. But here, this W value is the same W over here. It's still somehow the parameter that defines what our function is going to be, what our hypothesis class is. But now this X value is a matrix that contains all of the other X values just stacked upon each other like this. So the number of rows in is the number of data points. The number of columns D is the number of features that we have of this X matrix. And then Y is similarly defined to be the all the Y values just stacked upon each other like this. And especially in like statistics classes, statistics-y sort of people, they always write things out in this matrix form like this. More computer science-ish people, more likely to use this form over here. But these two things are just different notations for the same exact thing. Okay, we still haven't gotten to the super interesting stuff yet, but any questions just notationally at this point? What any of this means? How we went from equation 6 to equation 7? Yeah. So this L right here, if we just substitute in this L, then we'll get that that's equal to 1 over n, sum from I equals 1 to n. This L is defined as y hat minus y. Y hat is this thing on the left over here. So this is h of x sub I minus y squared. So that's just doing this substitution immediately. And now this h of x sub I, all the h of x sub i's have this form right here, w transpose times x. So one more substitution gives me the 1 over n, sum I equals 1 to n of the xi transpose w minus y squared. So that's what I have in green right here is the same exact thing right here. The question, any other questions notationally? What's going on? Okay, so for our purposes at this point, The reason we care about this least squares loss and this ordinary least squares regression model is that this is a particularly nice in-sample error that is easy to compute a minimum for. And so the very first problem right here on the next page says the ordinary least squares model is convenient because the hypothesis G, which minimize E sub n, can be computed in closed form. And so show this computation. So we're going to explicitly compute the G equals the argmin H in H E sub n of H. And again, this formula right here is the very first formula that I had on the page where I called this G the empirical risk minimizer, the ERM. And so we're going to find a formula for the empirical risk minimizer of the ordinary least squares model. Doing some substitutions, this is equivalent to saying W is equal to the argmin of W in R to the D of, again, substituting in that formula for E sub n that I have, 1 over n, sum from I equals 1 to n of the xi transpose W minus y sub I squared. And again, it'll be a little bit more convenient to say that that's the argmin W in R to the D of the x W minus y squared, like that. The textbook, again, uses G instead of H whenever the function is an estimate. So the G values are somehow estimated from the data. When we start talking about the parameter vectors, though, so here the W is somehow in like unique correspondence to these functions. Each function is uniquely defined by an individual W. And so sometimes we just talk about the parameters instead of the functions. And when we talk about the parameters, it's common, again, to put the hat on top of the parameter. So there's W hat, the weight vector that I am estimating from the data is computed by this, because this is going to minimize the squared error. Anytime we have a minimization problem, so from calculus, we know that the way we solve that is we take the derivative and set it equal to 0. So I'll say 0 equals, we take the derivative with respect to whatever we have down here, the variable that we're minimizing with respect to. So dw of this whole thing, xw minus y squared. This derivative it's not hard to do by hand, but we're not going to do it by hand. We are instead going to use the internet to have it tell us what to do. Wolfram Alpha is my normal resource of choice to skip annoying calculus computations. But Wolfram Alpha only works on one-dimensional things. It doesn't work with vectors and matrices. So instead, this website, matrixcalculus.org, works with matrices and vectors. Come back over to Firefox, click on this tab. I have matrixcalculus.org opened up right here. And there's actually a number of example functions that you can put in here. This one right here, a times x minus y, is so common that it's one of their examples. And so I have that up here. It's important to make sure that we're taking the derivative with respect to w right here and not with respect to one of the other variables. We're taking the derivative with respect to w, and this is our final result. If you were doing this by hand, it's basically that the same as if all of these were individual, just scalars, but then you just have to make the transposes line up right to make things well-defined. So this is our derivative. And come back over here. So that is, make sure that I get this written right, is 2x transpose times xw minus y, like that. And then our goal is to solve for the w right here. So we move this factor throughout all of this. That's equal to 2x transpose xw minus 2x transpose y. Move this thing over to the other side. 2x transpose y. There we go. Equals 2x transpose xw. Divide out those 2's, take the inverse of x transpose x, left multiplied on both sides, and we get that x transpose x inverse times x transpose y is equal to w. And so this right here is our final solution for w hat. This procedure of finding the a closed form solution for a particular optimization problem is a moderately common like machine learning technical interview question when applying for jobs. I happen to think it's not a very good one because it's not the sort of thing that often you do in the real world, but it, I don't know, demonstrates a reasonably robust knowledge of calculus. And so for that reason, interviewers like to ask it if they think you're weak on calculus or they want to test your calculus somehow. This formula down here is also one that we've seen before in this class. I had you calculate the runtime of computing this in our first lecture notes. And so if, again, our x is a in by d, and the y was in by 1, then I'm sure everybody 100% remembers, and I'll write it down here, what is the runtime of this? That the runtime is O of d squared in plus d cubed. And if it's okay if you can't just look at this and instantly know that that's what the runtime is, but my expectation is that given a sufficiently long amount of time, you would be able to figure out what you need to look up and figure out exactly what the runtime for a solution of something like this is. Any questions so far? Okay. So problem number 3 right here. It's asking, or it's telling us, it says the VC dimension is undefined for this ordinary least squares problem. And why is that the case? Well, the VC dimension is only defined for binary hypothesis classes. So by this, I mean that the output is -1, 1, sort of like the perceptron was. And our VC dimension, or sorry, our hypothesis class is real numbered output. So the VC dimension is just undefined. And so none of the tools that implies none of the statistical tools that we've talked about are applicable to this. is a very, very important point to realize that this VC dimension here seems like it might be applicable, but it's not. And so that that VC generalization bound that we were talking about just doesn't apply. There are many similar generalization bounds that people have developed for these types of problems. And actually the textbook talks about some of them. If you are in the data science major and you're going on to take the statistics class, you talk about some of them there. But based on the prerequisites for this course, probability is not a prerequisite. And so we're not able in this class to talk about the statistical properties of ordinary least squares. We're just focusing on the classification case. Any questions about that? Okay, one logical question might be then, why did we talk about this? Like, why are we why did we go through all of this work? Why did we solve this particular optimization right here and not a different one? And the answer is that this is essentially the only, the squared loss is essentially unique in having a closed form minimizer. All other loss functions that at least people care about in practice do not have closed form solutions and somehow require an iterative procedure to solve. It also turns out that anything that does have a closed form solution is basically just the squared loss kind of in disguise somehow. So it's really, in some deep philosophical sense, that is the only possible problem that has a unique solution, or that has a closed form solution. And by closed form, I mean there's just a mathematical formula that you can run and compute it. Every other possible problem, you must do some sort of iterative procedure, some sort of more complicated algorithm to solve. So this leads us to our discussion of the 0-1 loss and the computational properties of the 0-1 loss. So again, this is the loss that we have studied in depth statistically with the VC dimension. And so now we're going to talk about it at a high level, runtime wise. The textbook goes into a lot more detail here. This is, for our purposes, this is going to be a good source of true-false style questions, but it's not going to be a source of more complicated free response questions. And so these are these 4 bullet points that I have right here are the things that you need to know about the 0-1 loss. And I'm just going to explain them right now. So the first one, I already said it, 0-1 loss used by the perceptron has no closed form solution. And so because of that, we talked about the PLA, the perceptron learning algorithm, for computing one of these empirical risk minimizers. So the hypothesis G that minimizes E sub n, this whole thing again right here, it's just a long way of saying the ERM. But this only works when the data is linearly separable. And when the data is not linearly separable, the PLA will never terminate. It'll run forever. And so we're not going to talk about why that's the case, but you are responsible for knowing why that's the case. And so before the midterm, I would definitely recommend making sure that you look back at the algorithm and see why it won't terminate if the data is not linearly separable. Again, linearly separable data means that if you have your pluses and minuses, you can draw a straight line through it and it will separate it. That's the example of linearly separable, the classic one. That's the example of not linear separable. No straight line can separate that. At least in 2 dimensions, we saw that if we had a feature transformation, then we could separate it in a higher dimension. So number 3, the book introduces the pocket algorithm. Again, something you don't need to know in detail, but you need to know this fact right here, that this algorithm is not guaranteed to converge. to a minimizer of E sub n. No matter how much time you allow it to run, you can allow it to run like infinitely until the end of the universe, and it is still not guaranteed to find anything that approximately minimizes E sub n in any sense. You can't, there's just no bounds for it, essentially. And in general, this fact right here, minimizing the 0-1 loss is what we call NP hard. If you haven't heard of things that are NP hard before, I have a quick summary of it right here in this fact too, but definitely recommend that you watch this short 10-minute video right here. But this is going to be like a key source of true false open questions on the midterm, and especially it'll be a source of questions where the answer is open instead of true and false. So the idea here is that the best algorithms that we have for solving NP-hard problems currently take exponential time. And so this big O notation that I have written here, omega of 1 plus epsilon to the d, is the particular exponential runtime bound that we have on the 0-1 loss. Any possible algorithm for solving the 0-1 loss, or any currently existing algorithm solving the 0-1 loss. Most people believe this is a tight bound, believe this would be the best possible algorithm would have this bound, but we don't currently have a proof for that. And so it's possible, it's an open problem, whether there is a sub-exponential time algorithm for solving the 0-1 loss. Yeah, so I'll just read this last sentence. Therefore, finding the optimal runtime for directly minimizing the 0-1 loss is an open problem, and there is no meaningful known lower bounds on the optimal runtime. So that, again, will be a key source of true-false open questions, and definitely refer back to that when working on those problems. Main takeaway is that statistically, the 0-1 loss was great. Computationally, it totally sucks, and we can't do anything with it computationally. Any questions about that? Question is, can I go in more detail? Unless you have like a specific way of going more detail, then it would be like a multi-hour diversion. So, yeah. I'm just gonna like the fact that yeah, so this is some sort of, in some sense, a fundamental trade-off that we have here with the 0-1 loss, that we can pick something that is statistically good but computationally really bad. Is it possible for us to get something that is both statistically good and computationally good? And we'll say sort of in the next section, but it really is somehow like a fundamental trade-off that you can't get the absolute best in both cases.
So the reason that it costs so much computationally is because the greater, the more complex data sets you have, the higher dimensions you have to try to get something that perfectly separates it, and that costs more.
Yeah, the question is can we have some intuition about why this is what's the hard part about solving this? When we go through this logistic loss, I'll draw some pictures, and maybe that'll provide that intuition. Yeah. So good question. Hold on to it for a little bit. Question is, difference between NP complete and NP hard. Do you have to know anything about NP complete? The answer is that the difference between complete and hard doesn't come up at all, and so no. Okay, so the logistic loss. A lot of machine learning courses, this is like the starting point of the machine learning course, somehow talking about the logistic loss in many different variations. And there's a lot of things that can be said about this logistic loss. And yeah, so let's get started with that. The beginning part here is, again, more annoying notation, just slightly generalizing the things that we've said before, so that we can say something more meaningful about the logistic loss and how it compares to the 0-1 loss. And again, the reason, so this first sentence right here, the reason, our fundamental motivation for talking about this logistic loss is the 0-1 loss cannot be efficiently optimized. So we're going to find new functions that are somehow statistically really close, really similar to the 0-1 loss, but can be efficiently optimized. So this was our definition of the 0-1 loss right here. And this version of the 0-1 loss is only defined on the set -1 and 1 when y hat and y are equal to -1 and 1. And down in this little space right here, I'm going to draw a small little table of all the possibilities of y hat and y and this function right here. So these can only take -1, +1. So try -1, -1, positive 1, +1. And then the y value itself also -1, +1, -1, +1. So there's only 4 different possible inputs to this particular loss function right here. And the equation 8, if we plug in these 4 different inputs, again, the meaning of this formula, these square brackets, is that whenever y hat is not equal to y, we'll get a 1 out. Whenever they're equal to each other, we'll get a 0 out. So equation 8 here, when they're equal to each other, we get a 0. When they're not equal to each other, we get a 1. And these are the only 4 possible inputs and outputs to this particular function. What we're going to do, though, is we're going to generalize the definition of our loss function a little bit so that the y hat value in particular can take any real number. So we allow y hat right here, y hats in any real number instead of just -1 and 1. And we want to do that in a way where our new function agrees with our old function everywhere that the old function is defined. And this particular function right here satisfies that. So if we look at equation 9, then so y hat times y, whenever y hat and y are equal to each other, -1 times -1, that's going to be equal to +1. Y hat times y is +1. On this input right here, -1 times -1 is +1. That's greater than 0, so we get a 0 output for equation 9. Whenever y hat and y have opposite signs, -1 and +1, this term right here will be negative, and so this will be false. We'll come down here to the otherwise, and we get 1 and 1 when they have opposite signs, and then again, the same sign is going to give us a 0. So this version of the function is, in some sense, less intuitive than this version of the function up here, of this loss function, but it's more general. We can use it when y hat is in any real number, and so that's why the textbook's introducing it now, and why it's going to be useful for us. Any questions about that? Okay, then one more notation is that this y hat y is a super common thing to appear in our classification functions. And so we're gonna say that z equals y hat y, and then just define our loss function just in terms of this z variable right here. And that's what this q version of the loss is. Why it's the letter q, I don't know. The letter L for loss makes a lot of sense. Q, it's just a random letter of the alphabet. But q of z defined like this is the same thing as this, which is the same thing as this. So this doesn't in any way look like the original 0-1 loss that we been talking about since the beginning of the book. but it's in some sense equivalent.
So how is this any like better at doing?
Oh, so the question is, why is this better? Why have we done all this? And next page will say why. Yeah.
How is the logistic loss defined?
So the question is, how is the logistic loss defined? We haven't talked about a logistic loss yet. We've only talked about a 0-1 loss. All three of these functions are the 0-1 loss, just different definitions. So when you say the new 0-1 loss, which one of these are you referring to?
The equation that counts it, like, it feels like in that case, if y and y hat are both 0, the loss is 1. That would be
The question is, can y hat and y both be 0? And if it can, then shouldn't that be equal to 1? Our y variable is still restricted to be this set -1 and +1. It's only the y hat that's allowed to be different. And so if y hat is equal to y, then y hat must be -1 or +1. Yeah. Good question. Okay, one last comment about a little bit of intuition about this z variable right here. We talked previously about the margin of a classifier, that if we had some like data points like this, and we drew a line separating them, then the distance between the separating hyperplane and the data point, we called that the margin. When we were talking about the PLA algorithm and its runtime. This z is not technically exactly this margin, but it's pretty much like in 99% of cases, like modulo really weird technicalities, you should think about z as this margin. Z is like basically the margin. And in particular, you should think about this loss function as somehow like existing along that perpendicular, that line perpendicular, this line right here. That's this Q function exists along that line. That's like the range of the Q function, or the domain of the Q function. Okay, so now why have we gone through all of this weird notation changing? And that brings us to this page right here, another page with a whole lot of stuff going on it. At the top here, we have 3 definitions. We're not gonna go over them all one at a time. We'll go over them in turn. And this example 3 right here lists a whole bunch of different loss functions with, it'll turn out they have different properties that make them somehow in various ways close to the 0-1 loss. And so in certain situations, we might want to use one of these as a optimizing one of these instead of the 0-1 loss. Again, all of these functions here are defined in terms of like this Q form, where the input parameter here is the z. And again, you should be thinking about that input as like, how far away is my data point from the linear separation? So what we're going to do is for each one of these functions, we're going to graph it, take a look at what it looks like, and then consider these 3 definitions up here, how they apply to that particular function. So down here, when I graph it, the x-axis is going to be z. We'll have some spot in the middle like this. That's the 0 point on the z-axis. And then we'll start by graphing the 0-1 loss, which looks something like this. Whenever our z value is negative, then our loss is equal to this spot right here is 1. And then whenever it's positive, our loss is equal to 0. And the first one I want us to take a look at is the very first one on this list, the exponential loss. So e to the negative z. At 0, e to the negative z is going to be 1. So it's going to intersect right here. And then it's going to grow really, really rapidly to the left, exponentially rapidly to the left. Because as z gets more and more negative, we're taking the negative of z right here, so exponent of something really, really positive. So it's going to grow really fast, and then it'll somehow level off and asymptotically approach 0 down here as we go to the right. And this blue line right here is the exponent function, the exponential loss. This red one right here is the 0, 1 loss. Are there any questions about what I've drawn right here? Why these things correspond to the two loss functions, or what it is that I'm claiming to have drawn? Yeah.
What's going to be the value of the 0 loss function at 0?
Question is, what's the value of the 0, 1 loss function at 0? And when z equals 0, then this will be false, so it'll be 1. Turns out that it basically doesn't matter, but I'll go ahead and draw like the little circle thing here, so it's not equal to 0, and maybe I shouldn't have even drawn this vertical straight line, that it goes there, and then it discontinuity jumps down here and keeps going. So the first one of these definitions that we have is what's called a surrogate loss function. So a surrogate loss function, so in this case, Q is my surrogate loss function. Whoops, and this, so I guess that's a typo. Instead of L right here, that should be a Q. The Q and the L are somehow like, again, a bijection between them to say it formally, but you can go back and forth between the Q and the L. So people will informally talk about both of these loss functions as being the same thing. But to be a little bit more precise, this should be a Q right here. And it's any loss function that upper bounds the 0, 1 loss everywhere along the z-axis. And so this exponential loss, this one that we just drew like this, does in fact upper bound the 0, 1 loss everywhere. And so I'll go ahead and say, yes, right there for, is it a surrogate loss function? Yes. Are there any questions about what it means to be a surrogate loss function, or why this blue line is a surrogate loss for this red line? Okay, let's do another example here. Let's skip down to the logistic loss, this one right here. If we plot the logistic loss, what it's going to look like is it'll be a straight line like this, intersecting the one right here, and then kind of curving similarly to the exponential loss down to 0. This is the logistic loss in green. You don't need to know, like, I don't know, be able to plot these just in your head, but the intuition is that, like, as z gets really, really negative, then this term over here gets really positive. So this 1 doesn't really matter. So the log and the x basically cancel out. And so it's just a straight line. But then as this z gets really, really positive, then it's behaving just like the exponential loss. Again, this is a surrogate loss function because it is above the 0, 1 loss everywhere. And we'll do one more example, this smooth 0, 1 loss. This one, if you were to plot out this formula, what you would get is you would get something that looks like this. It's like asymptotically approaching 1 over here to the left, and then somehow swoops down, and then asymptotically approaches 0 over here to the right. That's the smooth 0, 1. And this now is not an upper bound of the 0, 1 loss. So this is not a surrogate. Any questions about those? Okay. So the next important property of our loss functions is going to be convexity. There's many different equivalent definitions of convexity. The one I wrote right here is somehow, or what I consider to be the most intuitive, the easiest one to look at visually. For the purposes of this class, we're not going to be needing to, or what you need to be able to do is just look at the graph of a function and determine whether it's convex or not. You don't need to resort to complicated definitions. So we say that a loss function is convex if the line segment between any 2 points on the graph of the function lies above the graph between the 2 points. That means that, as an example, this blue, this exponential function right here, if I pick any 2 points, so as an example, those ones and those ones, draw a line between them. That line is going to be above the graph, and that's true no matter where, no matter what 2 sets of points that I pick. So this blue line is in fact, or this blue curve is in fact convex. The exponential loss is convex. Same is true for the logistic loss. That is also convex. But the smooth 0, 1 loss, this is not convex. It's possible for me to pick, say, this point right here and this point right here, draw that line between them. And now portions of that line, in fact, the entirety of the line is below the graph. And so this one is not convex. Yes.
So it has to apply for all possible pairs of 2 points.
Exactly, all possible pairs of 2 points. That it is possible in the 0, 1 loss to pick 2 points where the line is above the graph. But it's not just, is there some pair of 2 points? It's all possible sets of points must be above the line must be above the graph. And so because we found some pair of points that is below the graph, it is not convex. Last, let's see. So why do we care about, before we talk about robustness, let's talk about the surrogateness and convexity and why we care about these 2 properties. First, let's talk about why do we care about the surrogate property. The answer is this fact 3 right here. Every surrogate loss function has the property that our training loss if we were to evaluate it with the 0, 1 error, the training loss is going to be less than or equal to the training loss on our whatever the surrogate loss function is. So we said before that the logistic loss is an example of a surrogate loss. And so the E sub n of logistic loss is strictly greater than or equal to the E sub n of the 0, 1 loss. And so while we can't optimize this thing directly, what we want is to make En small for the 0-1 loss. And while we can't do that directly, we can potentially make it small for a surrogate loss. And if we are able to make it small for a surrogate loss, then we know that the 0-1 loss is also small. And so if we substitute in this formula right here, this 12 formula into our VC dimension formula, then we'll have a bound on the 0-1 loss output. So that the classification error that we're getting, are we getting the right answer or not getting the right answer? And that bound depends on something that we can compute, the in-sample error of our surrogate loss plus this VC dimension factor. So that's why we care about surrogacy, is that we get this good statistical properties for surrogate loss functions. We care about convexity because it'll turn out that convexity allows us to efficiently optimize our loss functions. And so if a loss function is both convex and surrogate, then it is a potentially good one for us to use. There's this last property of robustness, which is something else that we'll also want it to have, but we don't quite have enough time to talk about robustness today. So we'll finish up talking about robustness after fall break. And we'll also talk about why convexity is good for optimization after fall break. But at this point, it should be moderately obvious that surrogacy is good for statistical properties. These other functions that I have not gone through down here, these are things that would be like great sources of questions on the midterm for me to ask about, like, is the hinge loss a convex function? So this would be a good table to fill out before the midterm. Any questions on anything that we've done? Question is, when is the project due? The answer is that the nominal due date is the end of the weekend, Tuesday after fall break. If you don't want to work on it over fall break, which I would encourage, you should. Breaks are for enjoyment, not for work. You can work on it beforehand, or you can collaborate and get the 2-day extension, and it'll be due Thursday. Question? Yeah, so question about office hours. Since I'm not available for the Friday office hours, I would be happy to come up with some additional office hours times. Off the top of my head, I don't know what would be good. But yeah, post a GitHub issue if you want the Wednesday office hours, and I'll figure out how to do that. Okay.